One last example of antiderivatives. We're going to look at a problem involving motion. Remember the relationship between position, so s of x, and velocity. Remember that velocity is the derivative of the position. And remember that acceleration is the derivative of the velocity. So that's stuff that we learned previously when we were studying derivatives. Now what we're going to do is kind of work these problems backwards. We're given the acceleration function for a particular particle. That acceleration is 6t plus 4, where t is the time, and let's assume it's in seconds. We're given that it has an initial velocity, so at time 0, its velocity is negative 6 centimeters per second. What does that negative mean? And its initial displacement at time 0 is 9 centimeters. So we're coming into the action where this thing has moved 9 centimeters and now our time clock starts. So we need to find the position function. So again, we're going to work backwards, but let's look at some relationships that we already know. The derivative of the position function is the velocity, and the derivative of the velocity is the acceleration. So the position is the antiderivative of the velocity. It's easy to get all twisted with these things. The velocity function is the antiderivative of the acceleration. So if we realize that the derivative of the velocity is the acceleration, then the derivative of the velocity is 6t plus 4. So what we want to do is work backwards from the acceleration, taking antiderivatives until we get to the position function. So the derivative of the velocity now is 6t plus 4, so we can apply our reverse power rule to find the antiderivative of the derivative of the velocity to get the velocity. You may have to listen to this one more than once. So using the power rule, we have 6t. So t, of course, has an exponent of 1, so we're going to add 1 to the exponent and divide by that new power. So we should end up with 6t squared over 2 plus 4t plus our arbitrary constant. And let's simplify that first term. We get 3t squared plus 4t plus c. All right, now that is the velocity function, which is not really what we're being asked for, but we want to find the specific antiderivative because we actually know something about the velocity. We know that at time 0, our velocity is negative 6 centimeters per second. So we can use that information at this point to solve for c. So now we have a good solid velocity function, 3t squared plus 4t minus 6. Now we can keep going from there. Remember, we have to back up to the position function. So remember, the velocity is the derivative of the position function. So if we take the antiderivative of the velocity, we'll get the position function. So t cubed plus 2t squared minus 6t is the result of taking the antiderivative of the velocity, plus d. And I've just used a different letter just to distinguish it from the velocity. It really doesn't matter what letter we use. It just stands for an arbitrary constant. But now we want a specific position function. We don't want the most general one. So we want to figure out, how do we get a value for d? Well, now we look again at our problem and we're given some information about the position. We're told that at time 0, our initial, that shouldn't be, sorry, that should just be 9 centimeters, not 9 centimeters over s. So if you plug that into the position function s of 0 and substituting a 0 where there's a t, you're going to end up with d equals 9. So our arbitrary constant is equal to 9. So you have s of t is equal to t cubed plus 2t squared minus 6t plus 9. So again, what we did is we worked this problem backwards, starting with the acceleration. We took the antiderivative of acceleration to get the velocity. We took the antiderivative of the velocity to get the position.